Going to go totally bust. Well, it looks like it's recording, so that's a good sign. What I want to do with you today is exactly the opposite of what we have done in previous lectures. In previous lectures, we looked at, for example, a reaction where we had a reactant A, which is converted or is consumed. And we wrote the rate equation for that. We said rate of A, or we can also say dA over dt, that's exactly the same, equals minus K times concentration of A to the power of m. And we said this here is the rate constant. This here is the rate order. And we have a negative sign. Oh, fall slowly, please. It's far more enjoyable. And the negative sign we have because A is consumed, so that indicates consumption. And we said the equation for, let's say, a first order reaction with this respect would be A final equals A initial times e to the power of minus k times T final minus T initial. Can you actually see this writing from the back? Yeah, okay, that's good. Excellent. Now, what if we have something like that? A is converted into B. So very clearly A is consumed, right? So A consumed. And B is produced. God, we've got lots of football fans here, huh? So how can we write this actually? For A, it's very easy. We can say dA over the, well, it's exactly what we had here for A. And if we look at the graphical representation of the whole thing, what does A mean again? A is the reactant in this scheme here. So that's the thing that is used. So we can draw a graph. And if it is a first order reaction, let's just for fun, let's just say we plot A versus time. Okay? What would you expect in terms of curve? It would be an exponential decay, exactly. So it would be something like that. Yeah? And this would be here A initial. Now, what would you expect for B? What happens to B? It would go up. And exactly, it would go like that. It's quite difficult to put that onto the mobile phone, you know. It's a rectangular hyperbole, exactly. So it would look like something like that. So that would be B. Yeah? Are you happy with that? That is what it looks like. Now, go away. Now, let's say we start with A initial. Our A initial, good morning, good afternoon. A initial equals 100. Yeah? And let's say our B initial equals 0. So we just have A at the moment and no B. And we wait for a certain time, and then let's say we have our A final is, let's say, 80. How much B final do we have? On your keypads? If you don't have one, can't be bothered to get it out. How much B final do we have? What do you reckon? 20? 20, 20, 20, 20? So we've got quite a few 20s here already. Yeah, you're absolutely right. You're absolutely right. We still have 80, so we are probably here. So that's 80. And we have 20 of the B here. So that would be 20. How did you actually do that? How did you come up with 20? Let's see if we can say 100 minus 80. So what you did was A initial minus A final. And that gives us our B final. Yeah? So, let's find out if we can come up A initial minus A final, exactly. So let's come up with something how we can very easily calculate B final. And we know that A final equals A initial times E to the power of minus K times T final minus T initial. So all we need to do is plug that into this, our wonderful equation. And we have, let me write it in a different direction. B final equals A initial minus A initial e to the minus K times, and I just simply write T. That's T final minus T initial. And what I can do now, obviously, is I can factor out A initial, and I can say B final equals A initial times what? One minus e to the power of minus K times, let's write it properly, T final minus T initial. So that would be the equation for our B. If we have a case like that, where we have A is converted into B. That makes sense to you? And we have always if you like, A final plus B final always gives us A initial. That was sort of our starting point. Yeah? Are you happy with that? I'm happy with that. If you are happy with that, then all is good. So here we were looking at the production of B. Which we can also almost refer to as B is growing, A is going down, B is growing. Yeah? That's one case of growth. There is another one, which is you need to sort of play around a little bit with this. I abbreviate it as B like that. There's nothing there that really produces B. But again, it's sort of a growth in this case. How could that be? Well, just think of two rabbits. Ideally, a male and a female rabbit. Yeah? So you have two rabbits, and they do what rabbits do. Wobble around, eat, do other things. And before you know it, you don't have two rabbits, you have four rabbits. And before you know it, you've got 8 rabbits. And so on and so forth. So again, it's growth, isn't it? How could we formulate that? Obviously, there is no A, there is nothing consumed apart from the rabbit marriage, if you get my drift. But, you know, nothing else is consumed. How can we write that? Well, we can write the rate at which the rabbits reproduce, rate of B, or we can write dB over dt equals. What sign would we need here? Is something consumed? What sign would we need? What do you reckon? Negative? So we have plus, minus, minus, plus, so that's 0. We've got another plus, okay, there's a slight tendency towards plus. What did we say up here, actually, when we looked at that? We said the minus here, that indicates consumption. But with the rabbits, there's no consumption. They're doing what the rabbits do. So it would be a plus sign. And very often, instead of writing a K, when it comes to growth, people use a different symbol for the constant. They very often write an R. And R times concentration of the rabbits to the power of M. Hopefully this looks pretty familiar, apart from the R and the K. So what we have here, that is our rate order. This here is our rate constant, or probably I should say, actually, growth constant. And the positive sign indicates that it is, in fact, growth, not consumption. Now, what we could do with that thing, with this equation, we could very easily convert that now into something more useful. And if we say, for example, for first order growth, we can say, well, our final rabbit population equals our initial rabbit population times e to the power of, and here's the only difference, plus r times t final minus t initial. The only difference to the consumption really was, apart from the r and the k thing, was the plus and the minus. Yeah, so that is the equation for growth. We might have some additional constraints here. For example, if you have 0.5 rabbits, you will probably not end up with a massive rabbit population, because usually half a rabbit does not reproduce. You also want to have the opportunity for things to actually being able to reproduce, if you look at a growth like that. So if you have 2 female rabbits or 2 male rabbits, even in the age of EDI, equality, diversity and inclusion, is not going to work. That has nothing to do with rabbits being not abiding by law. It's just simply is a biological fact. 2 male rabbits cannot reproduce. On the other hand, if you have some species that are, for example, self-fertilizing hermaphrodites, they would very nicely fit this scheme. What does it look like in terms of a graph? What would the graph look like for B in this case? B time what would it look like? Exponential, somebody says, goes like that. Does it go like that? No? It's carrying on. So, is that you are demonstrating a washing machine, or? You say it's going up and up and up. Well, what happens if you have a rectangular exponential hyperbola? Straight line, exponential. Oh, that's interesting. So what happens if you have, let's say, 400 rabbits and you wait for the next doubling? How many rabbits are you going to have? 800. What happens then if you have 10,000 rabbits and wait for them? How many? Flat. Straight. Does it go straight? No, actually what it does is, as the colleague says, it's exponential growth. It will go like that. It's an exponential growth. The rabbits will rabbit continuously. We can actually even determine what is the doubling time for the rabbits. Doubling time, very often, this is also abbreviated as T 2/1. T1/2, what was that? Loud? Yes, you are right. Did you hear that? Half-life. T1/2 is half-life. Doubling time is T2/1. But the great thing is, you don't have to learn anything new because nothing really changes for the doubling time and the half-life. The equation for the doubling time is ln2 divided by r, by our rate constant. So this allows us to convert r and a doubling time into each other. So for example, if I say to you that r equals 0.693 day to the minus 1, what is my doubling time? Sorry? Sorry? Ah! Okay, it's 1 day. Why? Because we have 0.693 divided by 0.693 day to the minus 1. And that, of course, equals 1 day. So here the doubling time would be 1 day. Some bacteria do that. They have a, compared to rabbits, they are fairly quick with the doubling. Does that make sense? So if you have a situation where you don't have an A that is producing something, where you basically write it in a shorthand form as this B with a whoop. I don't know how you would write whoop, but an exam. But if you use that, hopefully that makes sense. Then you can use a straight first order reaction. Of course, what we can do is, if we really want to know if it is a first order growth, what we can do is we can do B, L and B versus time. And what would we get if we did ln B? What do you reckon? Which way? So what you're saying is like that. Is that right? Yeah? Do you agree? Do you approve? Good. Yes, it is a straight line. What's this one here?
Oh, no, it's not.
That would be on your keypads. Give me what this circle is. Don't forget to put the UK in front of your message. What is this black blob? Wow. Must have something to do with ln, mustn't it? ln B initial. Are you sure about that? How sure? 99.9. Is that good enough? That point is actually ln B initial. You are absolutely right. Yeah? What is the gradient? You're absolutely right. The gradient in this case is R, our growth rate. So if we have a population that is growing, and we have the data for the growth, so we have 2 rabbits, 4 rabbits, 8 rabbits, 16 rabbits, God knows how many rabbits. And we plot these data, and we plot ln rabbits versus time, and we get a straight line going up. We know the rabbits grow according to a first order reaction. Yeah? Make sense? So, big question. If the rabbits grow so incredibly well, where are they? Where are the rabbits? Are we all rabbits? What happened to the rabbits? Sorry? They die. Oh, poor rabbits. Can't let them die. How are we actually going to write that? You're absolutely right. Why would they die, actually? Starvation, yeah. They hunting, yeah. They would, for example, not have enough resources. So we still have a situation, predator, prey, the cycles, disease, toxins build up, yeah, food, all these things. We still have B, they grow, but now the growth is no longer totally unrestricted. Actually, our growth rate or our growth constant is actually no longer a constant. The growth constant depends on the number of rabbits. In this case, growth constant, or I should say, well, sometimes it's called growth rate, but it's not the right thing. Growth constant depends on the population. In this case, B. Sorry?
So if they start dying, it's no longer a growth constant.
It's no longer a growth constant. The constant becomes a variable, which is a bit weird. Why is it called constant? Well, because it is still our R. Does anyone know what this is actually called? The first one, where they reproduce constantly, that is normal growth, logarithmic growth, or exponential growth. What is this called? That has a special name. Anyone? Exponential decay is a good try, but we are not decaying. The rabbits are still growing, but not infinitely. Non-exponential growth. But there is an element of exponential growth in it, but that's quite, I like that. Anyone else? No? It's actually called logistic growth. So, how can we write that? Now, let's try to figure out what it looks like first. We have B, that's our rabbit population, that's time. Right at the beginning, the rabbits will be happy as Larry. Do you actually know the favorite name for rabbits, for pet rabbits? What people usually call them, or very often? Does anyone have a pet rabbit? Bunnies? Yeah? Does anyone have pet bunny? You used to? What was the name of your? Huh? Ossox. Uh-huh. Most rabbits are called actually Stuart. Why? Okay, if you don't get it, the gentleman in the front here will explain it to you later. Huh? Oh, Keith, Fluffy. No, Stuart. You don't get that? When you introduce your rabbit, huh? That's evil. When you introduce your rabbit, hey, that's my rabbit Stew. Oh, thank you. So what does it look like? At the beginning, the rabbits will be very happy in reproducing. They will grow exponentially. We are on the same page here. Logistic growth means exactly that. R is no longer a constant. I think we need to have a talk later. You know, there's a good welfare service here. Not just for rabbits. So what you see, probably should be a little bit more careful with that. Let's draw it like that. It becomes a sigmoidal curve. So what happens here? Here, in this loads on campus, yeah, I know. In this phase here, we still have logarithmic. We have logarithmic No, don't do that. Don't do that. I know of some students who got kicked out of university because they tried to supplement their diet. They ate some of the bunnies here, and they also killed some of the ducks from the Keynes duck pond. Yeah, and somebody saw that and they got kicked out of university. It's not worth it. So that is logarithmic. Exactly, don't go hunting. Logarithmic or exponential growth. I could make now so many totally inappropriate comments about students and bunnies, right? But I don't. I like my job. But when we get more and more okay. Okay. We get more and more rabbits. We reach what is generally called the carrying capacity. Carrying capacity. That's the carrying capacity of the system. And that is usually abbreviated with a capital K. How do we get actually to the equation for this beautiful for this sigmoidal curve? Well, we can write dB over dt equals, it is positive, so we have a positive sign, plus R, that's our growth constant, but we have a modification to it. K minus B initial divided by K, and again K here is the carrying capacity, R is our growth constant, times B to the power of 1. That is the equation for logistic growth. I do not expect you actually to remember this for a test or something like that, but it's quite useful because there is quite a lot of stuff in it. What's in it? Well, we have the R and the B. That's perfectly, you know, that's something that we can deal with. But this thing here, I probably should take away this I. K minus B over K. Let's have a look at that. What happens if the population, if B is much, much smaller than K? If B is much, much smaller than K, we are somewhere here in this region. Leave him alone, right? Leave him alone. So if B is much, much smaller than K, we probably can even forget B. We have K over K, which gives us 1. So we would have B equals, or B final equals B initial times R E plus K R T. That's our normal logistic growth. What happens if B equals K? Loud? Is it 1? K minus B divided by K, if B equals K, what do we get? Run, rabbit, run. We get 0, don't we? So we have R times 0. So our growth rate becomes 0. When our growth rate becomes 0, what happens to the population? It's flat. There's no growth. Yeah? What happens if B is larger, much larger than K? What happens to K minus B divided by K? What's the sign? The sign will be negative. Which means that if we start, for example, somewhere here with our population of rabbits, what will happen to them? Negative growth. What is that? What is negative growth? It's consumption. So the rabbits will go down in an exponential decay. So with this logistic growth curve, we can actually predict what happens to a population. Did you know that humans follow logistic growth? Where is the carrying capacity for humans? 7 billion? 14 billions? What's that? Up? 100 billion? Too much. Actually, your guess is as good as mine. We have no idea where the carrying capacity for humans is. We don't even know whether we are beyond the threshold for the carrying capacity, whether we are now above the carrying capacity and things can only go downhill. We don't know that. Only future will show. There's also something that is quite interesting for biologists, because different species actually use different reproductive strategies. And we are talking about what is called the R strategists. R strategists are typically individuals or organisms that have a large growth constant. That means they reproduce very, very quickly. So their doubling time is very small. They reproduce. They are usually organisms that start in a new environment, in an ecologic niche, where there is no competition in this niche. So for example, there was a forest fire. Everything is wiped out, and the first kind of vegetation that you see comes from plants that are typical R strategists. They are not terribly well adapted to the environment, but they compensate that with huge offspring numbers. These are R strategists. In contrast to that, the K strategists, they are usually organisms that live very close to the capacity, to the range. They actually don't have a lot of offspring, but what they can do is they can look after the offspring longer. So it's not that they, for certain fish, for example, fish produce hundreds and thousands of fertilized eggs. Typical R strategists. Whales, on the other hand, they are, of course they're not fish, but whales are typical K strategists. They have only 1 or 2 calves per 5-6 years. Usually K strategists have a much longer lifespan than the R strategists. And K strategists are usually much, much bigger than R strategists. Where are humans? Humans are R strategists. Are humans R strategists? They could be a bit of both. You're absolutely right. Humans are actually somewhere in the middle, R and K strategists. At the moment, in Western Europe, it is pretty much the majority of the population follows a K strategy. When there is new areas to be settled, then very often people follow an R strategy. that means they have lots of offspring. That makes sense? So you see, even with a little bit of kinetic stuff, you can do quite a lot in terms of evolutionary biology. Actually, this concept of R and K strategy has been questioned recently, and actually there are new suggestions out there which talk about, for those of you who are interested in, about evolutionary game theory. So if you are fascinated by this topic like I am, have a look at this evolutionary game theory. No more inappropriate jokes about rabbits. Thank you very much, and I hope you enjoyed it.